Alright guys, here's our study guide help video for the Unit 6 test, which is coming up soon. So without any further ado, let's get started. For each problem, use a left-handed Riemann sum. And we're going to approximate the integral based off the values in the table. Now on your test, you're only going to be given either a left-hand or a right-handed sum. It won't be both. And these problems will only be worth 1 point. So when you're doing a left-handed sum, the first thing you want to note is that these distances here are the bases of your rectangles. So my first rectangle has a base of 3, so does my second one. The third one has a base of 1, and the last one has a base of 3. And when you're doing a left-handed sum, you start with the sides on the left, but you leave out the last one. And then you just do base times height, base times height, base times height, and base times height. And then you go ahead and just add all those up. And 24 plus 14, that would be 38, I think. But there we go. All right, let's go ahead and move on to the next one. All right. Number 2. Let's use a right-handed sum. Same exact process. The only difference is we're doing it on the right side. So we're still going to look at our bases, and bases are almost identical this time. But we're starting on the right side. So we use all these as our heights of our rectangles. And we leave off the one on the left. So base times height, base times height, base times height, and base times height. And we add all those numbers up, and we end up with a final answer of, drumroll please, 51. All right. Go ahead and move on to the next problem, number 3. So this one's asking us to use a trapezoidal sum, and it asks us to do 4 subintervals. Interesting. All right. So whenever they specify how many there are, like right now, if I were just to do this, we would have way more than 4 trapezoids. That would be 1, 2, 3, 4, 5. So as you guys can see, that's going to be a lot more than 4 trapezoids. So what they want us to do is they want us to break this thing up into chunks, so to speak. We want 4 subintervals. So whenever that happens, you have to do your last x value minus your first x value divided by the number of pieces that you want. And that means we're going to go for every third one. So we're really going from -6, add 3 to that, and you end up here. So what that means is I really don't care about this stuff here in the middle. So I'm just going to get rid of that stuff. Okay. And you're going to go ahead and continue that process. So we go up another 3, and then another 3, and another 3, and that gives me 4. And once again, let's go ahead and just get rid of the numbers in between each pair because we don't care about them. You don't have to erase them yourself, and I'm just doing this so it's easier to look at. So that's really all we care about are those chunks right there. All right? Let's go ahead and find these heights up here now. From here to here, all of my heights are going to be the same. These are the heights, by the way. I've already said it, but just to specify, those are the heights, and they're all the same. They're 3. And then these numbers here are the bases. So my first trapezoid is has a height of 3. So the way you find a trapezoid is you height divided by 2, multiplied by the sum of the bases. And the y values in this case are the bases. So that would be 20 plus 0. Okay, and then you're going to continue doing that for your other trapezoids. So the next one will be this group with a height of 3 and bases of 0 and 8. So 3 over 2 with 0 and 8 as my bases. Next one we'll do that piece. So once again, height is 3 over 2. Bases are 8 and negative 4. And then finally we have the last trapezoid, I think. It'll be this one. We have a height of 3 and bases of negative 4 and 2 being added together. And once again, it's okay if you just want to leave your answer like this, but if you want to go ahead and simplify all this, you can. So, I mean, well, technically you can't leave your answer like this. You would have to put a plus in between all these, indicating that you're adding them all together, and probably shouldn't be writing them vertically like this. It should be in a straight line. Anyway, that's the gist of it there. So you can leave it like that with them all written out as being added together, or you can simplify it. If you want to do me a favor and simplify it, makes it easier to grade. Not really. I still got to check your work, so it doesn't matter. But anyway, this one is 45. Comes out to 45 if you actually simplify the whole thing. So, all right, moving along. And that one's going to be worth 2 points. Doing trapezoid problems is a little bit trickier, and also because we're breaking it up into a certain number of subintervals. Let's go ahead and do the midpoint sum. Once again, you know, you have to break it up into 6 subintervals. So we're going to do, and I should really be putting up here equal subintervals, and I should have done that in the last one as well, so I think I'll fix that. But anyway, so we do the last minus the first, and this time divided by 6, and this time we're going to be going by 2's, it looks like. Now that's actually really convenient, and I'll tell you why. Now remember on the trapezoid how we didn't want to pay attention to those numbers in the middle? Well, not true when it comes to midpoint trapezoid. All of these numbers up here are the bases of each, did I say trapezoid? I said rectangle. So we're dealing with midpoint rectangles. Now these numbers up here represent the base of the rectangles, and the height of the midpoint rectangle is the y value that's in the middle there. So we actually end up here with a base times height of 20. And then the next pair would be base times height, which is 0. Base times height here is 10. Base times height is 0. So you just multiply the base times the 1 in the middle of each pair. Negative 12 it looks like. And then finally 2. Adding all these together, it looks like I'm getting 10 as my final answer. 45? I think not. I think that answer is wrong. I'll need to fix that. So we have 30, 32. I'm sorry. Oh, I forgot the 10, didn't I? So I think the answer is 20, actually. Let me fix that. 20 plus 10 is 30. Plus 2 is 32. Minus 12 is 20. So it's not 10, it's 20. But still, this answer is wrong here, so I'm going to fix that. And those ones are also worth 2 points. Now, the table, you'll notice when we did this one, since we were going by 2's, it already had the middle number in there. So that's nice. And it's kind of necessary if you're given a table problem. Now, if you're ever given an equation problem, you have to create your own table. You'll probably also have to create your own middle numbers. And we've seen some problems like that as well. But for now, this will be good enough. Let's move on to the next one here. Let's see. Which sum would give the least accurate estimation of a definite integral? The least accurate. Well, we talked about how midpoint sums and trapezoid sums are both better than left-handed sums. So we know that those are not going to give us the least accurate. Those will give us a better estimation than a left-handed sum will. Now we have two choices. I've got a left-handed sum with 20 subintervals and a left-handed sum with 10 subintervals. So another thing that we observed is that the more rectangles you have, the better. So since we're having 2 left-handed rectangles here, the one that has more rectangles will be a better estimate. So the one that will give us the least accurate measurement would be a left-handed sum with only 10 subintervals. So trapezoids and midpoints are always better than left or right-handed sums. And furthermore, more rectangles is better than less. In those cases, you'll get better estimates of the actual area under the curve. All right, go ahead and move on to property question. So we're going to have quite a few questions like this, I guess, on the study guide. I don't remember how many I put in here, but I do know that I'm only going to give you 3 of like these on the test, and there's going to be 1 point. So we talked about some various properties in lesson 6.3, I think it was. So you might want to get out your notes from 6.3 and look at those properties as I refer to them here. So for this particular problem, I want to find what is the integral from 0 to 10. Well, I know that from 0 to 7 is -5, and I know from 7 to 10 is 8. This one I'm not going to use at all because that's a g function. We want to look at that only. So you do have to pay close attention to what letters you're using. So I have one function that goes from 0 to 7 and one that goes from 7 to 10, but I don't have anything that goes from 0 to 10, or do I? It turns out because of property 5, going from 0 to 10 is the same thing as going from 0 to 7, and adding that to 7 to 10. Because the starting point matches that starting point, and the ending point matches that ending point, and these two integrals are connecting at a common place, which means that really they're just one big integral being split up into 2 pieces. And now that means then that the integral from 0 to 10 is going to be equal to this one plus this one. And since this one here is equal to -5, and this one here is equal to 8, then my final answer must be 3. So that's property 5. You don't have to tell me what property you used on the test, but I'm just doing it for your sake. I'm taking notes and watching this. All right. Now, before we even begin this, you'll notice that the limits are backwards. We've got the bigger number on the bottom and the smaller one on the top. So the very first thing I want to do is I want to apply property 2 and reverse those, which I'm allowed to do so long as I put a negative in front. Okay? So that's property 2. The next thing I'm going to do is I'm going to split this integral up, put it in brackets here, like this. Anytime you have 2 functions being added together in an integral, you can split it up into 2 separate integrals, but I'm going to keep that negative outside of the brackets there, because that negative is still there. And so whenever you separate the 2 pieces like that, I believe that was property 4, if I'm not mistaken. Next, we have another property we can apply here. This is a constant multiple. And when you have constant multiples, you could just remove those from the integral and put it in the front of the integral. And now we're ready to start substituting things. I have been kind of lazy here. I haven't been putting my 7 to 10. That's kind of important. Let me put that on there now. I've also been putting the x's on there. Lazy. It happens. Okay. So we have our negative. We have brackets. We have 3. And this piece, the integral of f from 7 to 10 equals 8. So I'm going to replace that whole thing with 8. And then the integral of g from 7 to 10 is 3. So we have 24 plus 3 is 27. And there's that negative in the front. The final answer is that. So once again, you guys don't have to necessarily show every single step. I mean, I don't think I'd be really very comfortable on some, like this problem in particular, just seeing you go straight from here to the answer. I'd want to see some kind of calculation happening. Some of the problems, though, you could probably really literally do them in your head, like the last one we did. So I'm not going to be too picky about the work here, but I would ask you to show some work if you can. But no, you don't have to go through and label each property and do one step at a time. That's not necessarily required. But you know, just try to show work when you need to. Try not to do it all in your head. You know, show some of it, like especially for these longer ones. Like this one was pretty long; it had multiple steps. But I'm not going to be real picky about this. All right. Next we have this. So I'm still going to apply property 4 again, where we write this as two separate integrals. Now this piece right here, we know the answer to that is 8. But this piece right here, we can apply property 6 to that. And property 6 says that anytime you're integrating a constant function, that constant goes in the front, and in the parentheses next to it, you put the two limits being subtracted. The order does matter. The one on the top comes first, and the bottom one comes second. And then my final answer is going to be 3 times 3 is 9 plus 8 is 17. All right. Then we have a u substitution problem here. So we're going to let u equal x minus 3. We're going to take the derivative of u with respect to x, which just so happens to be 1. So therefore du equals dx if you get dx by itself. And then by doing our u substitution, I'm going to replace the x minus 3 with a u. And I'm going to replace the dx or the du. And don't forget, we also need to change these limits. So if you plug the 10 in for x here, 10 minus 3 is 7, so the 10 becomes a 7. And if you plug the 3 in for x, you get 3 minus 3 is 0. So we're looking for the integral of f from 0 to 7, which we know to be -5. That is another type of problem you might see on your test. All right. Now we're going to transition into a whole different question. So the image of f of x below consists of a linear function, probably this piece right here, two semicircles, that's here, and a constant function. I don't see two semicircles actually. I see one semicircle, and I see two quarter circle pieces. So I think I'm gonna have to go back and change my direction. But we want to evaluate each of the integrals that follow. So I have to shrink that up a little bit so we can see all the questions. But we'll go and do this now. Of these types of questions, I will be picking 4 questions like these below. One of these each down here. And they're each worth 1 point. Okay? So let's go ahead and begin. Now, a lot of times with these questions, it's going to help us to go ahead and find all the areas that we possibly can to begin with, and to go ahead and label them on our graph. So let's go ahead and do that really quick. Okay, so let's start finding some areas here. So for this, the first thing you want to do is start breaking this thing up into familiar geometric pieces. All right, so we see here that this little rectangle is 2, and since it's under the x-axis, it's going to be -2. The semicircle down here has a radius of 1. So the way you find the area of a circle is pi r squared, but it's a semicircle, which means it's half of a circle, so it's actually just going to be pi over 2. Draw an arrow because they don't really have room to squish that in there. Same thing here, this triangle. The area of a triangle is base times height, so 1 times 1 is 1, cut in half, so it's 1/2. And since it's also under the x-axis, that will also be negative. This one here is actually the same, but it's just above the x-axis. So that one will be a positive 1/2. We have another rectangle of 2. Here we've got a quarter circle that has a radius of 2. So once again, you do pi r squared. But this time, since it's a quarter circle, we divide by 4. And that leaves me with an area of pi. This one is 2 also. That's another rectangle of 2. This is a ramp, and we talked about how to find the area of the ramps. You do the area of a ramp is equal to the area of a square of the same length minus the quarter circle of the same radius. So in this case, my ramp has a base and height of 2. So my rectangle has a base and height of 2, and so does my semicircle or quarter circle has radiuses of 2. So the area of my ramp is going to be equal to 4 minus the area of a quarter circle with a radius of 2, which is actually the same thing as I had here. So that's just going to come out to be pi also. So this ramp here is 4 minus pi for its area. And then the last rectangle has an area of 4. All right. Now we're ready to go ahead and start answering all the questions that they're going to ask us here. So if I'm going from -4 to 0, that would be all of this area here. Triangle. So that's what they're asking about on part A, going from x equals -4 to x equals 0. And that's going to be all these little areas added together. So the negative pi over 2, the -2, the -1/2, and the +1/2. So the answer to part A is going to be -pi over 2 minus 2 minus 1/2 plus 1/2. And you don't have to simplify this if you want. Part B. Now we want to do the area from +2 to +4. So that's right here at +2. After the +2, we want to go up to +4. So that includes the rectangle there, but it also includes this ramp right above it. So it's going to be 4 minus pi plus 2. All right. Part C. We're going from 0 to 8, but as you guys can see, it's backward. So the first thing we're going to do is we're going to reverse those numbers, and we put a negative in the front. Next, we're going to go ahead and find the area from 0 to 8. So 0 starts right over here, and then 8 is here. So we're basically finding all of this area here, all from 0 all the way over to 8. And we can find that just by adding all those pieces together. So that's going to be 2 plus pi plus 4 minus pi, running out of space here, and then the 2 and the 4, I'll just put those together to save space, plus 6 there. This one's actually pretty easy to simplify though. The pi's cancel, and 2 and 4 make 6, and 6 and 6 is 12 with a negative in the front, and -12 would be the final answer on part C. Alright, let's go ahead and move on to part D. So once again, you have to look for those properties where they're applicable. We get to do some more properties here on part D. On part D, we're going to do property 4, where we're going to apply the integral separately to the f of x and also to the 2. Now for this one here, we could apply property 6, which is where you take the 2 and you multiply it by the difference of the limit. This one, we're just going to do the geometry. We're going to look back up here at our graph, and we're going to go from 4 to 8, which is basically just this rectangle here. This is 4. And once again, this one's not too hard to simplify, so I think I'll go ahead and simplify it. 8 minus 4 is 4, and 2 is 8, plus 4 is 12. All right. Go on to the next question. So for part E, we're going to be doing the integral from 0 to 4 of f of x plus 2 dx. All right. So said we're going to do u substitution on this one. So that's our hint. So let's go ahead and do our u sub. Don't forget you have to change your limit, right? I'm going to plug 4 in here. That becomes 6. And plug 0 in there as well, and that becomes 2. So now the problem becomes the area under the curve of f from 2 to 6. So we're going simply from 2 up to 6. So now that's interesting because they're cutting this last rectangle in half. So it's going to be 4 minus pi plus 2, and we're going to stop right here at another 2. So altogether, that's going to be 2 plus 2 is 4, plus 4 is 8, and then the minus pi will be the final answer there. All right, now F is something we didn't really talk about in class, so I'm not going to require it on the test. I might throw it on there like maybe an extra credit question or something. Actually, not that hard, but it's just something to talk about. It's kind of like a ball coming at you from left field there. All right, so what we're dealing with here is, although we did talk about absolute values in this chapter, we didn't talk about them in this context here. So we're going from negative 4 to 0. So let's take note of that first. But what is it that absolute values do? Well, absolute value takes all of the values of your function and makes them positive. So all the y values, which is what f of x represents, all the y values become positive. So basically, if you kind of wanted to draw this really quick here, let me clean this up a little bit. The absolute value is going to cause all the y values to be positive. So the semicircle will flip up here, and it will come down like that. And so this piece down here won't even exist if you do the absolute value. Because absolute value just takes everything that's negative and flips it up so all the y values become positive. And so basically if you do that, all the areas that we have would also become positive. There would no longer be negative. So basically when you have the absolute value, when you're finding the integral of an absolute value function, basically you do the same thing. You just add all these numbers together. But the only difference is that when you do, the negative numbers don't exist. You just stick strictly to positive. So it's going to be positive pi over 2, positive 2, positive half, and then this one's already positive, so we leave it as positive. Okay, so that's all absolute value does. Not a big deal, but once again, I'm not going to make that a required question, just because we didn't include that in our lesson that we went over already. But maybe an extra credit, we'll see. All right, let's go ahead and take a look at the last part of this set, part G. Part G is asking us to find the average value. How do you find the average value of the function on the interval from 4 to 8? Well, the average value of a function is, we're going from negative 4 to 8. You just find the integral of it and multiply that by the distance between your limits. And that's, if you're forgetting what lesson that is, I think that was lesson 6.6. So that's how you find the average value. So this is going to be 1 over 12. And then this part is just area. So we're going from -4 all the way up to 8. So basically that's just adding all of these pieces together, right? And if you're going from -4 to 8, then you're going here, coming all the way over to 8. So just the whole thing. But we do have that 1/12 in the front, right? So we have 1/12 multiplied by -pi/2 minus 2 minus half plus half plus pi plus 2 plus 4 minus pi plus 2 plus 4. So it's just basically all the pieces together. And once again, you don't have to actually simplify this, write it out. Definitely good enough. All right, so that takes care of number 10. All right, so number 11, evaluate this integral. We have no way to integrate this using our standard integration strategies, but the way we learned about it in this particular instance, we recognize that this is not just any old equation here. This is actually the equation of a half circle. And so what you want to do is you want to recognize what your center is. The center is the x value, is the number that's being subtracted from x, but there isn't one in here, so you could think of that kind of like 0. So that would be your h value. You've got to remember, though, that that value is always the opposite sign of whatever it says, but in this case 0, the sign doesn't matter. And then whatever number is being added outside of the square root, that's your k value. In this case, that's not there either, so they're both 0. So my center is 0, 0. And then you also need your radius. My radius is the square root of this number right here, so that would be 10. And then we're ready to graph it, keeping in mind that this is the bottom half of the circle because we have a negative there. So my center is 0, 0, and my radius is 10, so I'm going to go left 10, right 10, and since it's the bottom half, down 10. And draw our little semicircle. And the last thing we need to do is pay attention to our limits. We're going from 0 to 10. So I really only want this much of that semicircle, which is actually a quarter circle now. The way that you find the area of a quarter circle is you do pi r squared divided by 4. That's for a quarter circle. And my radius is 10. And so if I simplify this, we'll end up with 25 pi. It's actually supposed to be a negative 25 pi. And the reason for that is because it's under the x-axis. Okay? And so that would be the value of that integral. So you have to recognize these equations as half circles. We don't have any other strategy to do those. So here's another one. For this one, my h value is 4. Remember, you'd always do the opposite sign of whatever's here. My k value is 10. So together, that makes up my center. And my radius is going to be the square root of this number right here, which is 9. So, drawing my circle then for 10. About here-ish. And then my radius is 9, so I'm going to go right 9. $13. So if I go right 9, that puts me at 13. And if I go left 9, put me at -5. And since this is a positive square root, we're going to go up 9, which will put me at 19. So I'll just kind of cheat and say, okay, fine. So it's a half circle that looks like this. And then lastly, we want to pay attention to our limits. I'm going from -5 to 13, so that's from here to here. And what we have is a semicircle with a rectangle underneath of it to find the area, which is represented by this integral. So the rectangle has a height of 10 and a base of 18. And so the area of that rectangle is 180. Now for the semicircle here, it's going to be pi r squared over 2. And so you end up with 81 over 2. So the total answer for this integral then, the area under the curve, would be 180 plus 81 pi over 2. That's that. Okay. Evaluate each definite integral. There will be one question like number 13, 14, or 15. So in other words, you're going to have a question like this, or like this, but you'll only have one of them. You won't have all three of these on your test. And that question's only going to be worth 1 point, right? So let us begin. I think we're going to need a little bit more writing space for this one, so shrink it up a tad. All right, so what's important here is that you know how to find the integral of a piecewise function. We're going from -7 to 3. So we're going to start at -7, but we have to stop at -3 because this function gets broken up into two pieces. So on the interval from -7 to -3, we have our first piece, which is this. And then after that, we're going to pick up where we left off. We left off at -3, and then we're going to keep going until we get to our last value, which is +3. So the interval from -3 to +3 is this last piece here. All right. So this piece is pretty easy to do. We have a property for that. According to the property, we take the number that's inside and we multiply it by top minus bottom. Save ourselves a little bit of time here by applying property 6, and that gives me -18. This one, on the other hand, is going to take some work. We have to do the fundamental theorem of calculus with it. So step 1 is to integrate the function. So I would have x squared over 4. That negative stays in the front. When you integrate this, you're going to add 1 to the power, so it becomes 2, and then you divide it by 2. Since there's already a 2 in the denominator of this term here, when you put another 2 down there, it becomes 4 because you multiply those together. And then minus, since that's just a constant there, we can just put an x next to it. Yeah. Now, we're going to go ahead and apply the fundamental theorem of calculus, which says that we can go ahead and split this up into two pieces. One where we plug in the -3 and one where we plug in the -7. And then from there, we're going to simplify it. So we end up with -9 over 4 plus 27 over 2 minus, oops, I don't like how I wrote that. Sorry, let me back up a little bit. Minus negative 49 over 4 plus 63 over 2. And then we're going to go ahead and distribute this negative. And after you distributed that negative, you can go ahead and get rid of all the parentheses and brackets and everything. It's going to become a negative 63 over 2 now. Distribute the negative. Then you combine your like terms. So negative 9 and 49 makes 40. So if I put these two together, I get 40 over 4, which reduces to 10. And then this next one here, if I do 27 and 63, what will that give us? Put these together, that's going to give me negative 36 over 2, which is negative 18. And then finally, that's negative 8 altogether. So this is the answer for the first integral. It was negative 8. We applied property 6 to the second integral to get negative 18. And so adding those together for my final answer, I get negative 20. All right, so let's take a look at another one. This one is an absolute value question. Now, when it comes to absolute value questions, the first thing that you need to do is you need to change it into a piecewise function. And you do that by setting the part that's inside the absolute value equal to 0 and solving. And what that finds for you is it finds you the cusp, the place where the absolute value goes from being instantaneously positive to being instantaneously negative. So there's my cusp, and we're going to go ahead and do a number line. 1 is here. And we pick a number to the left, and we're going to plug it into the original problem. So I'm going to pick a number that's less than 1. So let's do 0. And we take the absolute value. And as you guys can see, when x is less than 1, we get negative numbers, and the absolute value will change the signs of the outcome. If you pick a number that's greater than 1, it probably will do the opposite. Let's see if that's true. Yep. So I'm going to put NC here for no change. And so I want to rewrite this absolute value function as a piecewise function, a function that's been broken apart into 2 pieces. The first piece is going to be everything that's less than 1, and the second piece is going to be everything greater than 1, and you're going to put an equal sign on one of them. It doesn't matter which one you put it on. We've decided that for the one that's less than 1, the absolute value will change whatever's on the inside of the absolute value bars. So for all x less than 1, we're going to put negative 3x plus 3, opposite signs. But for all x greater than 1, we don't change the signs. So for all x greater than 1, the part inside the absolute value bars does not change. Okay, and so there is our piecewise version of this absolute value function. Now we're ready to continue with the integral. So my integral starts at negative 4, and it ends at 2. But before I can get to 2, we are on our way from getting from x equals negative 4 to x equals 2. We have to stop at 1. Because on the interval from negative 4 to 1, we are doing this piece of our function. And then we're going to pick up where we left off. We've left off at 1, and we're going to keep going until we get to the last part, which is 2. And on the interval from 1 to 2, we're using this piece of our function. So when you're integrating a piecewise function, you have to integrate it according to the pieces. You start at your first point, you stop at your first cusp, and then you pick up where you left off and finish off at the last point. All right, so that's the second step. So step 1 is to rewrite it as a piecewise function. Step 2 is to break apart your integral into the pieces. Step 3 is to go ahead and just do the integration. So I'm going to go ahead and begin the integration process here. That's going to give me negative 3x squared over 2 plus 3x. And this one will be the same thing, just opposite signs. And we don't want to forget to put our numbers here on the outside. All right. And then from there, we're going to go ahead and calculate it. So you're going to need a lot of space for this. First of all, I would start by making two separate sets of brackets. The first bracket's going to be for this one, and the second one's going to be for this one. And as you can see, they're connected by a plus. So I made two really big brackets. Now for each bracket, you're going to put two sets of parentheses in there with a minus in between them. This is just getting us ready for that fundamental theorem of calculus, where we plug the numbers in and subtract the outcomes. So I'm going to plug in 1. Now, this is going to take me a minute here, so I'm going to pause my recording, and then when I unpause it, you'll see everything plugged in. All right, so there's everything that's been plugged in according to the fundamental theorem of calculus. Next thing that we're going to do is we're going to simplify inside the parentheses. So you do your exponents first, then your multiplication. So you're going to have negative 3/2 plus 3 for the first set of parentheses. For the second one, we're going to have 16 times 3 is 48, divided by 2 is negative 24, minus 12. Next one, we're going to have 6 minus 6. And then for the next one, we're going to have 3/2 minus 3. So after you've simplified inside the parentheses, my next suggestion is to go ahead and distribute any negatives that you see. And after you've done that, you're going to get rid of all the parentheses and stuff. So we just are going to have negative 3/2 plus 3. And then this is going to become a positive 24 now, and a positive 12. The 6 and the 6 are zeros, so those are just going to cancel. I'll just ignore those. And then negative 3/2, and then positive 3. All right, and then you start combining everything you can. Like I see these two fractions here have the same denominator. So I'd say let's combine anything that has a common denominator already to save us some work. Negative 3 and negative 3 makes negative 6. So we have negative 6 over 2, which is negative 3. And then you just add all these normal numbers together. So 3 plus 24 is 27, plus 12 is 39, plus 3 is 42. And so then when you combine these, you end up getting the final answer of 39. And I made a mistake. So I had to go back and do this problem again, actually, myself. There's just so many places to make boo-boos along here. So the key to success is neatness. Number 1, be neat. Number 2, use this strategy that I'm sharing with you about the brackets and the parentheses. It's a nice way to organize your work and get everything set up. And then finally, follow the order of operations that I gave you here. Parentheses first, distribution second, combine last. Easy. Parentheses, distribute, combine. Make things a little bit easier. All right, that's just how I found. But still, even following that, I still run into boo-boos. You just got to be really careful. And that's where the neatness comes into play. If you're not neat, then you're not going to catch where your error happened. So you have to be neat so that when you do make a mistake, you can easily go back and find it. All right, let's go ahead and do one more. Now, on this last problem, I'm not going to be asking you guys to actually evaluate it. I'm just going to be asking you to write it as 3 separate intervals. Okay. So, but the process is pretty much the same as the last one. It's just that it's a little bit more complicated because we're dealing with a trinomial instead of a linear function. So, once again, you set the part that's inside the parentheses equal to 0. And in this case, you're going to want to factor it. I know I've noticed that some of you guys just don't want to do the factoring, so you keep using the quadratic formula. You can do that. It'll work.
But I think factoring is pretty useful in a lot of different situations. I would definitely encourage you guys to master that at some time soon. Very useful. So I end up with two cusps. So that's one of the differences about working with trinomials, is that you have the potential to end up with more than one cusp. So we have a -3 and we have a -2, and that means we have three intervals. My first interval is anything less than -3. My next interval is in between -3 and -2, and my last interval is greater than -2. And we're just going to be plugging in a test number from each interval. So, for instance, tell you what, I'm going to cheat a little bit here. You guys can do it too, but you got to be careful with it. But what you do is we're going to pick a number greater than 2. Now, a number that's greater than -2 is 0. 0 is a wonderful number to plug in. So I'm going to plug in 0. 0 is fun to plug in because it just makes everything go away. You really don't got any calculations to do. So as you can see, we have an absolute value of 6. And the absolute value bars are not going to change the sign of that number. So on the interval from x is greater than -2, the absolute value function does not change the signs. And what that means then is that the next interval will change, and the other one after that won't change. That's usually how it goes. It kind of follows like an AB pattern. So once you know one, you know the others probably. Now, just to be safe, I would encourage you guys, if you have time, to check by plugging a number in. But I would say about 90% of the time, if not more, that's how it's going to work. All right. Let's go ahead and move into making our piecewise function now. So for my piecewise function, as you can see, we're going to have three pieces. We're going to have the first piece be for all x less than -3. And for all x less than -3, there's no change to the number inside of the brackets. My next piece is from -3 to -2. And for that piece, we do change the signs of the numbers that are inside the brackets. And then finally, my last piece is for all x greater than -2, and that piece does not change. There's my piecewise function. And now we're ready to just set up the integrals. We're not going to actually we're not going to find the value of the integral. All we're going to do, according to the directions, is just to rewrite it as the sum of three separate integrals. So this integral here can be rewritten as an integral that starts at -5, and it keeps going until it gets to our first cusp. And on that interval from -5 to -3, we're on this piece, so we're going to put this piece here. Plus, and then we move on to the next integral. So we start where we left off at -3, and we move on to our next cusp, which is -2. And on the interval from -3 to -2, we're using this piece. And then on the last one, we're going from where we left off, from -2, up to our last point, which is 0. And on the interval from -2 to 0, that's my last piece there. So that's x squared plus 5x plus 6. And so that's as far as we're going to go with it. I want to see that you guys know how to find the cusps and how to rewrite this integral as three separate integrals. And now, yes, technically you could, if you wanted to, do the fundamental theorem of calculus on all three of these to get the final answer. But on your test, I'm not going to require that, simply because of the amount of time it takes. It would be far too long, and it's just not worth it. So we'll leave that off for now. But anyway, so that ends numbers 13, 14, and 15. On to a new question. For this one, we're being asked to find the average value of the function on the given interval. You can use your calculator on any problems on this test to check your answer, because I did show you how to do that in the lessons. However, on every problem on this test, you do need to show your work. because on the AP exam, some questions allow you to use calculators and some don't, and I want you guys to know how to do it both ways. So use the calculator to check your work, but make sure you know how to do it by hand. So the average value of a function can be calculated using this formula. Where A and B are the numbers of your interval. So setting this up then, I would have 3 minus 0 here, 0 to 3 here, and 2x plus 1 here. So out here, that's easy. That's just 1/3. And to find this, we're going to have to integrate what's in the integral there. So the integral of this is x squared plus x. We're going from 0 to 3. There's my setup again, right? Brackets with parentheses being subtracted. And we're going to plug in our 3 first. And then we're going to plug in our 0. Now the 0 just goes away. 3 squared plus 3 is 12. And 12 times 1/3 is 4. So the average value would be 4. We're going to do another average value question, but this time it's giving you a different type of function. So we go 1 over b minus a, integral of -3 e to the x from -3 to 0. All right, so this piece here just becomes 1/3. Now when we integrate this, the -3 is just going to stay right where it is. And as a matter of fact, before I do it that way, we could handle it a little bit differently too. We could actually take the -3 out first. And I think I'll choose to do that. And the reason I'm going to choose to do that is because these multiply together quite nicely to become just -1. Now to do this piece, the integral of e to the x is just e to the x. And so now doing the fundamental theorem of calculus, don't forget your -1 in the front. We have e to the 0 minus e to the -3. Any number to the 0 power is 1. And e to the -3 is 1 over e cubed. And then you're just going to go ahead and distribute this in there. And you're going to get -1 plus 1 over e cubed. And I would say just leave your answer like that. We don't need to go any further. All right. Let's go ahead and move on to our next question here. So notice that they've given me an integral function, and they're asking me to find the derivative of it. Now, whenever you have just a number down here and an x right here, the way that you're going to find the derivative is actually pretty darn fast. You're just going to use the second fundamental theorem of calculus. When you take the derivative of an integral, the integral just goes away, but that thing on the top comes in and replaces the t. And that's it. Boom, you're done. Pretty sweet. Right? But that, you can only have it be that simple and fast when there's a number down here and an x here. Okay? If it's any different, then we're going to have to do it a different way, which I'll show you in a second. But for now, that's the second fundamental theorem of calculus. So here's another one. If you wanted to find the derivative of that one, once again, the derivative of an integral cancels out the integral, and the x will drop in the place of the t. And so we're now getting this second fundamental theorem of calculus. But once again, I can only do that because I've got a number here and an x up here. Yet anything else than a number and an x, then that's no good. You have to do next strategy. So notice this one is a little bit different. We don't have a number and an x. We've got a number and an x cubed. Now this is what I would call a composite integral function. And when it comes to composite integral functions, what we talked about is if you want to find the derivative of this, well, the first thing you would do is you would integrate this, but then you're going to take the derivative of it. So it's kind of like the integral and the derivative cancel, so you really just end up with the same thing all over again, right? But because of the fundamental theorem of calculus, you get the same thing written twice, being subtracted from each other. You'll notice I'm leaving a blank here, and that's for a reason. And the reason for that is because you're going to be plugging the x in, the x cubed, I should say, first, and you'll also be plugging in the 4 for the second one. And when you since this is now a composite function, you also need to multiply it by the derivative of the thing you just plugged in. So the derivative of x cubed is 3x squared, and the derivative of 4 is 0. Now, anytime you have a 0, that piece just goes away. And so my final answer here would be 3x squared over x cubed minus 3 cubed. So there was a little formula I gave you guys if you'd rather use the formula rather than the thought process that I just went through there. The formula was that if you have an integral function with a function down here and a function here and a function in here, then the derivative will simply be the I function subtracted from itself twice, with the h of x plugged in the first spot and the g plugged into the other, and then the derivative of those inside functions multiplying by it. So if you'd rather just use the formula, you can. I like to think my way through the problem because it's a hard formula to remember. There it is. All right, so let's take a look at number 21. So using our little formula once again for the derivative, I'm going to get this function here written twice. For the first case, I'm just going to put parentheses right now where the t is. For the first set, you're going to plug in the top number. In the second case, you're just going to plug in the bottom number. And then we also multiply it by the derivative of the number we just plugged in. So the derivative of x squared is 2x, and the derivative of x is 1. Now you can leave it like this, or you can simplify it. It really doesn't matter. I might not simplify it all the way. And I don't see any like terms except for these 6's. Those can be combined and they cancel each other out. So I see the final answer here. If you wanted to simplify it all the way, you would get this. But so long as you were neat and I could see what you did, you can leave it up there like that too. Okay? All right. Let's see. And we have another one. All right. So at this point, I'm starting to feel like this is a little bit overkill, but what the heck, we'll do one more. All right, so once again, we want to find our derivative of this integral function. So we're going to write this equation twice. With a subtraction sign between them. We're going to drop these values into the parentheses now. And then we're going to multiply by the derivative of those values. And that's that. All right. So That does it for integrals of, or derivatives, I should say, of composite integral functions. All right, let's move on to another question here. You'll have one question like this. It'll be worth 1 point. Oh, and by the way, with regards to the last set there, you will have where'd it go? You'll have 2 questions like these. One of them will probably just be one of these basic ones where you just do the second fundamental theorem of calculus, and the other ones will probably be like one of these ones where you have to do that little formula. All right, let's go ahead and take a look at number 23. There will be one question like this. So they give us a graph of f prime, but they're asking us questions about f. So how do I go from f prime to f? And the answer is with an integral. So if I integrate f prime, then that gives me f. And if you integrate f prime on an interval, then you can do the second fundamental theorem of calculus. I'm sorry, the first fundamental theorem of calculus, and that's what we're going to do. So they give me the x value of 2, so I'm going to call that my starting point, but we want the x value 5. Now, when you do this, make sure you put the bigger one on top and the smaller one on bottom. You don't have to, because we can use property 2 to fix it later if you don't, but if you just set it up right at the beginning, you won't have to do property 2. Okay, so then by the first fundamental theorem of calculus, the integral of f prime from 2 to 5 is equal to f of 5 minus f of 2. That's the FTC, the fundamental theorem of calculus. Now, this, though, we can find this by doing the area under the curve from 2 to 5. And so what we want to do is we want to find the area under the curve from starting here at 2, going all the way over here to 4. Now you can find that as an area of a trapezoid, or you can find it as the area of a rectangle and a triangle, whatever's your preference. I'm going to go with rectangle and triangle. They're both 2, it looks like. And so that's going to be a total area there of 4. So the integral of f prime from 2 to 5 is 4. They give us f of 2 is 3, so I'm going to replace this with 3. And we're trying to find f of 5. And so if I just add 3 on both sides, I can find the missing value that I desire to have. And that would mean that it is 7. There you have it. That ends part 1, and we'll move on to part 2 now.